Alright, so let's take a look at problem 2.35. I think this will be good to work at least part of this out as an example problem for us. Now, this is out of the Bannatyne textbook, and we're in our strain life chapter, and we're looking at different damage parameters that are sensitive to mean stresses. And in this particular problem, we have a nickel-based alloy under 4 histories, 2 of them at R is equal to -1, and 2 at R is equal to 0. And we are supplied with the strain amplitudes for these histories. We were given material properties, and then we were given some test results. And we want to compare predictions using the 3 methods, and then we want to take a look at the test results and compare our predictions or our calculations to these test results. Just as a word here, if you've already done the test, what you do is a calculation. If you haven't done the test yet, then what you do is a prediction. If you already know the answer, then you can't really predict it. But we're going to make a comparison, and we're going to go through our methods, and you'll see that if we understand how this problem works, and I think this will help you with other problems. First thing we need to do, though, is let's get a better idea of what this particular problem is asking. So we have 2 types of strain histories. One strain history is it's strain controlled R is equal to -1 with an amplitude of 0.005. So what that means is this distance, which is the range over 2, is 0.005, and it goes to plus 0.005 strain down to minus 0.005 strain, and it continues on. So delta epsilon over 2 is equal to 0.005. And so our strain range from, say, here to here is going to be equal to 0.01. So this is the R is equal to -1 situation. Of course, in case B, we just have a bigger value of the strain. Now we have to be a little bit careful in case C and D. Case C and D involve what are called R is equal to 0 loading. If you remember, R is defined as the minimum divided by the maximum. In this case, in strain controlled loading, this refers to our minimum strain divided by our maximum strain. So by R is equal to 0 loading, I know that it goes to 0 each and every cycle. Now here I have to be a little bit careful because it tells us the strain amplitude is 0.005. Remember, the strain amplitude is half of the range. In this case, the range is from here to here. So the amplitude being 0.005, the range is going to be 0.01. Okay. D, there's a similar situation. Okay, I'll let you figure out what the maximum strain should be. So the mean strain here is 0.005, and that means our maximum strain is 0.01. The R is equal to 0. Again, that gives us a strain range of 0.01. Now, along with this problem, we need to find the mean stresses. So for each of these, we're going to have to do a hysteresis loop calculation. The initial branch of the hysteresis loop will use our branch equation, or we'll use our initial Ramberg-Osgood equation using the cyclic stress strain curve properties. It's going to use this equation. We're also going to need to calculate the hysteresis branches. the hysteresis branches will use this equation, our hysteresis branch equation. And we will need to calculate if we have any mean stresses or not. I think we're going to see that in the r is equal to -1 loading, we're going to have a 0 mean stress, but we are going to have some mean stress in the r is equal to 0 loading. All right, so we need to do these calculations. Now for all these types of things, I like, when I work these problems out, I like to put them all in a spreadsheet. I have my spreadsheet here, and I have various tabs, so I would encourage you to set up a similar type of spreadsheet for your homework, and this will help you with some of the other homework problems as well. You could do all this by hand and a root solver on your calculator. Spreadsheets come in really handy. So here's the problem statement, and here are some of these equations that we're going to use. Manson-Halford, Morrow, modification, Smith-Watson-Topper. I have tabs for each one of these. I have a page here where I just have the equations, which basically we've seen before, but I also have the addition of the initial hysteresis excursion and the hysteresis branch equation here. And I'm going to show you another technique with Excel. We're going to use Newton-Raphson for some of this, but we're also going to use something called a solver. Now, in order to activate a solver in Excel, we have to go through a little process here. I always forget, so I also just put in the instructions right here into this spreadsheet on how to activate the solver. But basically, you go to File, Options, Add-ins, Excel Add-ins, Go, and make sure that this box is checked where it says Solver Add-in. You may also want to check Analysis Toolpack has some other features in there that you may end up using. I don't know why they just don't make this by default, but maybe the default business use doesn't really have a need for solvers. I don't know. But you have to go through this business in order to be able to use the steps that I'm going to show you next. When you do that, say you're on the Home tab, when you do that and you get over to Data, then this will suddenly appear, this solver thing right here. So here's my Ramberg-Osgood equation. Here's for the initial loading. Let me put that right here. And here's for the branch equation. And my inputs are the strain and the amplitude into the branch equation. And these aren't necessarily the correct values. I also have the strain life equation. We're going to talk about that too. But here are my material properties. Notice that my E is written in terms of megapascals to be consistent with the K prime and the values of stress that I'm going to put in. Okay, now let me show you how to use the solver, and then I want to talk about a problem that I had when I first tried to do this that I had to overcome and reshoot the video and everything. So when you use a solver, here's our equation. Epsilon is equal to sigma over E plus sigma over K prime to the 1 over N prime value. So here's a guess. I'm going to guess maybe 100 for my sigma. And here's my equation for what I call the right-hand side. If I go to the equations, that's this one right here. This is the right-hand side for the initial excursion. And here's my epsilon, 0.005. Now, this column has the epsilon value minus the right-hand side. Now, if this were to be 0, if I were to guess the correct value of stress, this error value would be 0. Okay, it's not 0. You can say, well, that's pretty small, but we can make it even smaller. And we can find the right value of stress. So we're going to use the solver. Now, to do this, I'm going to hit the solver button, and I am going to set my objective to be this cell, and I'm going to set it to a value of 0. Okay. You're going to have some options here. Make sure it says value of 0 by changing the variable cell, this one. Okay. And so that drove it even smaller. So it looks like my stress that corresponds to this value of strain is 899 megapascals. Let's make a new page. So this is going to be 0.005 in 899. This is from the blue equation. This is the initial curve. Okay, now we need to use the hysteresis branch equation. The hysteresis branch equation is going to use a strain range of 0.01. It's going to use an amplitude of 0.005. All right, so by the same reasoning, I'm going to use my solver. Okay, see now I'm using the branch equation. Delta sigma over 2 over E plus delta sigma over 2 over K prime to the 1 over N prime. I'm going to use my solver. I'm going to drive this cell to 0 by changing my delta sigma cell. And I got 1798. I'll talk about the error here in just a second. So I have a delta sigma of 1798. So where do I end up? If I'm at 899 and I'm having a decreasing branch, I'm going to subtract 1798. I get down to minus 899. So now I'm at minus 0.005 and minus 899. If we were to go on the upslope, it would do the exact same thing, and this should be symmetric and everything. We end up with a mean stress of 0. How do we calculate our mean stress? We take the maximum plus the minimum divided by 2. In our case, it's 899 minus 899 over 2. Our mean stress is 0. Our maximum stress we can find in one of two ways. The way they show in the Smith-Watson-Topper equation is you take your mean stress and you add the stress amplitude for that hysteresis loop. The stress amplitude is half of 899 times 2. It's half of 798. 1798. So we have 0 plus 1798 divided by 2. That is 899. Of course, when you look at this plot, that makes a lot of sense because we're at 899. So we need to remember these values, 899 and a mean stress of 0. 899 for the maximum. Now, just for fun, I also have a strain life calculator on this page using no mean stress correction whatsoever. Remember how this works. Let me put in some number here. Sigma f prime over E times 2nf to the B plus epsilon f prime times 2nf to the C. And here are all of my numbers that I have for this. So by the same reasoning, I'm going to use my solver. I'm going to change this cell to a value of 0 by adjusting this one. And I get 23,372 reversals. 2nf is reversals. Okay, now here's the error that I got. I had used an old version of Excel when I developed the spreadsheet. and it couldn't find solver32.dll. So here's a handy tool that I like to use, this tool called Everything. You can find it on the internet. It's free, and it searches your computer for solver32.dll. It was hiding in this folder in the Microsoft Office program directory. I copied that and I put that into my working directory for my spreadsheet, closed everything down, restarted it, and it somehow found it. And I haven't been able to reproduce the error, but if you do get that error, that's how you can overcome it. Okay. So hopefully you don't have that problem and everything's just working just fine. Now let's look at some of these equations. Let's go back and look at the strain life equation, the Morrow, manson-halford, and Smith-Watson-Topper. If we look at the Morrow equation and sigma's mean stress, sigma naught, is equal to 0, then we obviously get back to the strain life equation. If we look at this equation and sigma naught is equal to 0, we get sigma f prime or sigma f prime to C over B, we get back to the strain life equation. It's not so clear that that's the case for the Smith-Watson-Topper, and we're going to do some calculations and see what happens. Now, we can set up the equations the same way and use the solver. I just happen to have my Newton-Raphson iteration set up for these things, so we're going to go with that for the Morrow, manson-halford, Smith-Watson-Topper mean stress corrections. And each of these have their own tab. So we're going to look at the Morrow first. And let's go back to our equations. I call this the right-hand side, and this is the strain amplitude. So the right-hand side is sigma f prime minus sigma naught over E, and then all this stuff over here. Okay, here's the equations here. Sigma f prime minus sigma naught, which is 0 in our case, with an amplitude of 0.005. The way the Newton-Raphson works, you take an initial guess. Let's say it's 1,000 cycles. I calculate the right-hand side, which is the right-hand side of this equation. And then here is the right-hand side minus left-hand side. I'm going to try to drive this down to 0. Here's my derivative, and my updated guess is going to be the old guess minus this thing over the derivative. All right, so 2196. I won't say all of these, but again, I'm just using the Newton-Raphson iteration technique. And it should be starting to drive us toward an answer. And you know what's going on here. That shouldn't have driven it that way. I'm not sure what button I hit. But it looks like we have 23,372. 23,372, which is the same as what we had in the basic strain life equation. All right, manson-halford. Mean stress is 0, amplitude here. Let's put in 1,000, let's put in 10,000 cycles. We're going to use the same technique. And we have converged 23,372. Now it's really hard to say that any of these fatigue lives should be calculated to any more than 3 significant digits. So please keep that in mind. I may write down more digits. I won't count fractional reversals. It doesn't make any sense to do that. But, 3 significant digits on reversals is probably all we're going to get. So in the end, we'll probably show this in scientific notation with a limited amount of numbers behind the sign over here. All right, so 23,372 for Manson-Halford. Now let's go to Smith-Watson-Topper. Okay, our maximum stress is 899. Let's see, let's just double check that. Based on our sketch pad, we said our maximum stress was 899. I guess I label this a strain life, but strain life based. So this is my Smith-Watson-Topper. We have sigma f prime squared over e plus 2nf to the b. Excuse me, 2nf to the 2b plus sigma f prime epsilon f prime 2nf to the b plus c. Here is my right-hand side, my left-hand side. And my new guess is based on this cell, the guess here minus this cell over the derivative. So I'm adjusting this. And again, you don't have to use the Newton-Raphson technique necessarily. I want to emphasize this because it's something that you may end up programming in if you're using Fortran or C or whatever that doesn't have a built-in root solver. Okay, so it looks like we've converged at 23,126. Okay, and that's this value here. Okay, so we don't get exactly necessarily the exact same result that we get with Smith-Watson-Topper and with the zero mean stress. Should be pretty close, and it is, but it's not necessarily the exact same number. Alright, so I'm going to let you do History B by yourself, but let's do History C. History C is 0 to maximum with an amplitude of 0.005. Let me save this page. And let's make some room. Okay, now the amplitude is 0.005, so in History C, this value is 0.001, and actually I messed this up. This one goes down to here. Now for History D, okay, the amplitude is 0.01, so I guess that would bring our maximum up to 0.02. All right, so keep that in mind when you do that part on your own. All right, our first step is we're going to use our hysteresis monotonic Rambert-Osgood with the cyclic stress strain properties, where epsilon is equal to 0.01, and we're going to put in here sigma over E, sigma over K prime, and 1 over N prime. And we're going to solve for sigma. I'm going to go back to my spreadsheet. And I'm going to use my solver. I'm going to drive that value to 0 by changing this value. 1039. My initial branch. Gives me to 1039 megapascals. Now my delta epsilon is going to be 0.01. It's the strain range from here to here. So I'm going to go and I'm going to use my branch equation with a strain amplitude of 0.005. See, I put that in red to help remind me. This is the amplitude version I'm using. Let's put in some number. Here's my branch equation. Delta sigma over 2 over E plus delta sigma over 2 over K prime to the 1 over N prime. And use my solver. I'm going to drive that to a value of 0 by changing this one. And I have a stress change of 1798. Okay, so I'm up here at 1039. I have a range of 1798. I get down to minus 759. So here at 0 strain, I'm at minus 759. Now on the way up, I'm at 0, I go to 0.01. That's a strain change of 0.01 again. Well, what that's going to do is I'm going to get back up to here. Let's calculate our mean stress. It's 1039 plus minus 759 divided by 2. I get a mean stress of 140. Our stress range is 1798. Our maximum stress, well, it ought to be 1039, but let's check. It should be the mean plus the range divided by 2. $1039. Of course, those are all in megapascals. Okay, so that does check out. So I get some sort of hysteresis loop that just keeps cycling between 1039 and minus 759 megapascals. All right, with that information, let's go and figure out these values. So I said we had a mean of 140. So let's go to the Morrow equation with a mean of 140 and an amplitude of 0.005. Okay, I'm going to put in 10,000 for my guess. So here is my new guess: 13,872, 15,488, 15,657, Okay, so 15,659. 15,659. Manson-Halford. Mean stress of 140. Amplitude of 0.005. Initial guess 10,000. $52.82. Okay. Smith, Watson, Topper. Now here we have to be a little careful. In this, my input is the maximum stress. And let's see what we said that was. 1039. With the amplitude of 005. I'm going to guess initially 10,000 reversals. If I said cycles earlier, I should have said reversals. I'm doing my Newton-Raphson iteration. Looks like I get 12,944. Okay, so 12,944. All right, so this is how you can figure out these values, and this is something that you need to be able to do. Okay, in our fatigue calculator, at the very minimum, I'm going to have you do just the basic strain life equation, just using the strain amplitudes for identified cycles. But in other situations, you may need to implement, for your extra part, you may implement a Morrow, Manson-Halford, or Smith-Watson-Topper. I am going to let you do B and D on your own. So let's see, I think that is the majority of what we wanted to talk about for this particular problem. You know, beyond doing these calculations, do the compare part, do the discussion part, and remember, I'm looking for something more than it says, yeah, it looks good, or whatever. Try to be quantitative and try to use these results to gain a little bit of insight. These test results and these calculations may not be universal, but at least now you have the tools that you can kind of start to gain some more insight into what goes on with these various damage parameters and how effective they might be in comparison to the actual calculations.